Hello, welcome to another module in this massive open online course. So, we are looking at different kinds of, we are looking at convex optimization problems, and in more specifically we are looking at the specific class of convex optimization problems, which is basically linear programs. Okay. We have looked at linear programs and also demonstrated a practical application of a linear program, alright. And in this module, let us start looking at a variation of that or an extension of it, known as the robust linear program, alright. So, what we want to look at in this module is another interesting extension of a linear program, and which is also very useful practically, that is robust linear program. And linear program, if you remember, can be formulated as follows, that is, we want to minimize A bar transpose X bar. This is our objective function, which is an affine objective, and this is subject to the constraint of, again, an affine constraints, that is C bar transpose I X bar less than or equal to di for I equals 1 up to L. And now, however, while formulating this linear program, we have assumed this constraint, that is the C bar i's, that is, if you look at these vectors, okay, we have assumed these to be perfectly known. Now, remember, these can be perfectly known. Now, remember these C bar i's, these vectors C bar I which characterize this problem, they depend on the problem, right. For instance, in our base station cooperation, they are basically the power gains, all right, the gains between the base stations and the various users, all right. So, these have to be estimated in practice for any particular problem, which means naturally that there is going to be a certain level of uncertainty, or there can be a certain level of uncertainty in this. So, what happens in, as we have seen many times before, in practical scenarios, and this is especially, that is what we have said, it has a lot of practical relevance, there can be uncertainty in this C bar I. Alright. So, and there can be various levels of uncertainty. Now, there can be various models for this. Now, one interesting way or one practically useful model for such scenarios where there is uncertainty C bar I is to assume that these C bar i's are random in nature. Okay, alright, and this also gives rise to a stochastic linear program, a stochastic version of this linear program. So, one can assume that these C bar i's are random in nature. In particular, you can assume that these C bar i's are Gaussian, these are Gaussian random vectors with their nominal value, which is their mean equals mu bar I, and the covariance, that is, if you look at these C bar i's, C bar I minus mu bar I, C bar I minus mu bar I transpose, this is equal to R I. This is the covariance matrix, you can say this is the covariance matrix. So, and remember, the covariance characterizes the spread around the mean, alright. So, this is a vector, I am simplifying this for a scalar. For instance, if you have a Gaussian, alright, that this is your mean mu I, and as the variance decreases, it becomes more and more concentrated on the mean, alright. So, C bar I is a Gaussian random vector, the nominal value, or let us say the estimated value of this is mu bar I, that is the vector, and the covariance matrix characterizes the spread around that. If the covariance matrix let us say the eigenvalues, or if the variances of these different elements of C bar I are low, it means that it is very close to the mean. If the variances are large, it means that it has a large spread around the mean. Okay. So, basically that characterizes this problem, and of course, when the covariance matrix tends to 0 or becomes very close to 0, it reduces the previous version, because in that case C bar I becomes equal to mu bar I, that it is equal to the mean mu bar I with probability 1, and it again reduces to the deterministic linear program that we have seen before. Okay. So, now for this stochastic linear program, or this linear program in which the C bar i's are random, how do you formulate the, now if you look at the constraints, let us go back and take a look at the constraint. The constraint is C bar transpose I into x bar is less than or equal to di. Now, if you look at this, C bar is random, in fact C bar is Gaussian, x bar is a vector, correct. Now, therefore, C bar I transpose x bar, this is also random because C bar is a random vector. So, this implies this is random. Okay. And in fact, you will realize something interesting, that this is, you can also say that this is Gaussian. Reason being, C bar I is a Gaussian random vector, C bar I transpose x bar is a linear combination of the components of this vector C bar I. When you linearly combine Gaussian random variables, you get another Gaussian random. Therefore, C bar, there is a linear transformation of Gaussian random variables yields another Gaussian random variable. Therefore, C bar I transpose x bar is a Gaussian random variable, in fact, alright. And what you can see more interestingly, since this is C bar I transpose x bar I is Gaussian random variable, C bar I transpose x bar, this belongs, or this can take any value in minus infinity to infinity. That is the other interesting thing. So, remember C bar I transpose x bar previously was a deterministic quantity, now it is random. So, it can take any value between minus infinity and infinity, which means that it need not be less than or equal to di for some values, that is there can always exist some values of this vector C bar I where this exceeds di. One cannot, because of the random nature of this constraint, one cannot hope that this constraint is always satisfied in the optimization problem, alright. So, because this is random, need not or cannot be satisfied all the time, because it is varying randomly, cannot be satisfied. This cannot be satisfied all the time, which means this only holds with a certain probability. I can expect this to hold. So, this holds only with some probability. So, only holds with some probability. Let us say the probability is eta. So, what eta I, what we mean by that, or let us say this is beta I. So, what, or eta I, let us say the probability that C bar transpose I x bar less than or equal to di has to be greater than or equal to eta, which means what we are saying is very interesting, the probability with which the constraint holds, that this you can only talk in terms of probability. So, this constraint holds with probability eta, that is what we are saying is this constraint need not hold all the time, but it can hold with a very high probability, that is the probability with which this constraint holds has to be greater than or equal to eta I. For instance, eta I can be, let us say 95%. Just take a simple example, which means that this constraint has to hold 95% of the time. Okay, so eta I can be let us make it 0.95. Okay, 95% or 0.95, which means this constraint has to hold, which means this constraint holds 95% of the time. Okay. And therefore, now I can modify this linear program. Now I can modify this optimization problem. I can write this as minimize A bar transpose x bar plus b, subject to the constraint that the probability C bar I transpose x bar less than or equal to di greater than or equal to eta I. Okay. I equals 1 to up to L. So, this is your modified stochastic. You can call this as robust LP, or you can call it as a stochastic because the constraint is random in nature or holds with a certain probability. You can also call this as robust LP because you are ensuring that you are taking the uncertainty into C bar I into account. Now, let us modify this problem further. Now, let us look at this quantity C bar I transpose x bar. If you look at this quantity C bar I transpose x bar, we have already said that this quantity, this is a Gaussian random variable. Now, let us find the mean and variance of this Gaussian random variable. We have expected, mean is simple, expected value of C bar I transpose x bar. This is expected value of C bar I transpose times x bar, or which is equal to expected value of C bar I is mu bar I. So, this is mu bar I transpose x bar, which is equal to x bar transpose mu bar I. So, this is the mean. This is the mean. Now, what is the variance of this? What is the variance? The variance is the expected value of the random variable, that is C bar I transpose x bar, or you can write it as x bar transpose C bar I. So, x bar transpose C bar I minus its mean, which is x bar transpose mu bar I whole square. Now, I can write this as expected value of x bar transpose C bar I minus mu bar I whole square. Now, this is a scalar quantity. So, I can write this as expected. So, I can write it as the quantity into itself or quantity into its transpose, because this is a scalar quantity, x bar transpose C bar I minus mu bar I. This is a scalar quantity, or basically it is simply a number. So, this is simply a number. So, this is therefore equal to expected value of x bar transpose C bar I minus mu bar I times its transpose, which is C bar I minus mu bar I transpose times x bar, which is basically expected value of, I can take the x bar outside. So, this is x bar transpose, and now you have something interesting, expected value of C bar I minus mu bar I times C bar I minus mu bar I transpose into x bar, and this is equal to x bar transpose Ri into x bar, where Ri, you can see this is the covariance, that is expected value of C bar I minus mu bar I into C bar I minus mu bar I transpose. So, basically the variance of this C bar I transpose x bar, or x bar transpose C bar I, this is x bar transpose Ri into x bar, that is the variance of this quantity. Okay. And therefore, now what we have seen is x bar transpose C bar I, this is Gaussian with mean x bar transpose mu bar I and variance x bar transpose Ri into x bar. Okay. And now let us find, remember our constraint involves a probability. So, now let us find what is the probability that x bar transpose mu bar I is less than or equal to d. So, therefore, x bar transpose C bar I is Gaussian. Alright. Now, let us go back to the constraint and find what is the probability that this, let us simplify the probability that x bar transpose C bar I is indeed less than or equal to di. Now, if you look at that, the probability x bar transpose C bar I less than or equal to di, this is equal to the probability. Now, x bar transpose, let me subtract the mean x bar transpose C bar I minus x bar transpose mu bar I less than or equal to di minus x bar transpose mu bar I. Alright, I am subtracting the mean x bar transpose mu bar I. Now, I am going to divide by the variance. Remember, divide by the square root of the variance. So, this is the variance, and standard deviation, you can think of this as sigma square. So, sigma equals standard deviation equals square root of x bar transpose Ri into x bar. And so, therefore, this is equal to the probability, divide both sides by the standard deviation. This is equal to the probability that x bar transpose C bar I minus x bar transpose mu bar I divided by square root of x bar transpose Ri x bar is less than or equal to di minus x bar transpose mu bar I divided by square root of x bar transpose Ri into x bar. And now, if you look at this, quantity, what we have done is, from a Gaussian random variable, we have basically subtracted the mean and divided by the standard deviation. So, that gives us a 0 mean unit variance Gaussian random variable, which is nothing but the standard normal random variable. So, this gives us, this manipulation has given us the standard normal, what we call the standard normal RV, that is Gaussian random variable, mean equal to 0, now the probability that this is less than or equal to this is 1 minus the probability that this is greater than or equal to this. So, this is equal to 1 minus the probability that this quantity x bar transpose C bar I minus x bar transpose mu bar I divided by square root x bar transpose Ri x bar is greater than or equal to x bar transpose mu bar I divided by x bar transpose Ri into x bar. And now we have probability that the standard normal random variable, Gaussian random variable mean 0, variance 1 is greater than or equal to some threshold, that is given by the Q function, alright. So, this quantity is nothing but the tail probability of the standard normal, which is equal to Q of d minus x bar or di minus x bar transpose mu bar I divided by under root x bar transpose Ri x bar, very elegant, and this quantity is equal to 1 minus that, 1 minus the tail probability, and therefore the probability, and that is what we are saying, right, this is the tail probability, that is a probability standard normal, if you remember Q of x equals probability x greater than or equal to x, where x is your standard normal. That is Gaussian random variable with mean 0 and variance unity, and we need this probability to be greater than or equal to eta. So, this means this quantity is greater than or equal to eta. So, therefore, what we have is if you look at it, what we have is the following thing, the probability x bar transpose C bar I less than or equal to di greater than or equal to eta, this implies that Q of di minus x bar transpose mu I divided by x bar transpose Ri into x bar square root, this has to be, or 1 minus q, I am sorry, 1 minus q has to be greater than or equal to eta, okay. And this implies that q of x bar transpose mu I divided by square root x bar transpose Ri into x bar is less than or equal to 1 minus eta. Now, the Q function is a decreasing function. This implies di minus x bar t transpose mu bar I, sorry, this has to be all mu bar I over mu bar I over x bar transpose Ri x bar, this has to be greater than or equal to q inverse 1 minus eta, okay. Since the q function is a decreasing function, the inequality gets reversed. So, if this has to be less than or equal to this, that implies that this quantity has to be greater than or equal to q inverse of 1 minus eta. And note that if eta is greater than 0.5, that is the reliability with which this has to be hold is greater than 50%, then this q inverse 1 minus eta, this is greater than or equal to 0. So, this quantity is greater than or equal to 0 if eta is greater than or equal to 0.5. Okay. Let me just simplify this now further into something that is interesting. Remember, Ri is a covariance matrix, so Ri is a positive semi-definite matrix, so I can factor it as Ri tilde transpose this implies x bar transpose R I x bar equals x bar transpose R I tilde transpose x bar, and if you look at this, this is nothing but R I tilde x bar norm square, and therefore square root of x bar transpose R I x bar equals norm of R I tilde transpose x bar, and therefore the condition above this implies that d I minus x bar transpose mu bar I over square root of x bar transpose R I x bar, which is nothing but norm R I tilde transpose x bar is greater than or equal to q inverse 1 minus eta, which basically implies that, again, q inverse 1 minus eta is positive. So, you can write this as R I tilde transpose x bar is less than or equal to d I minus x bar transpose mu bar I divided by q inverse of 1 minus eta. Okay. And now, if you look at this, you will observe something interesting. You have here a norm, and here you have something that is affine. So, you have norm of vector x bar something, all right, norm is less than or equal to an affine function of x bar. Remember, this represents a cone. So, this is a conic constraint. Okay. So, this represents a cone and this is equal to a conic . So, this will become a cone program. So, this implies what with the robust linear program that we are talking about, this becomes a cone program, implies, or the stochastic LP, you can call it the stochastic LP equals a cone program, it has conic constraints. Okay. And therefore, now you can formulate this stochastic LP as follows, that is basically minimize A bar transpose x bar plus B subject to the constraint that your norm R I tilde transpose x bar is less than or equal to d I minus x bar transpose mu bar I over q inverse 1 minus theta for I equal to 1 to 12. In fact, this can be eta I, it does not really matter, this can be eta I. I am just going to correct this over all places. It can be a common eta or it can be eta I. Okay. You might want different reliabilities for different constraints. All right. So, this can be there you go. So, it is eta I and you can correct it everywhere to eta I, and this has to hold for I equal to 1 to up to L. So, this is your linear program. You can think of this as a robust version. For the scenario when these vectors C bar I are random in nature. Alright, so that is another interesting flavor. In fact, I can say this is a practical flavor of the traditional linear program. The linear program itself has several practical applications. This, in that sense, it makes it more practical or immensely enhances its utility by making it more relevant, because in several scenarios these coefficients C bar might not be known accurately, or might be known only with a certain degree of accuracy. In particular, when they are random and they can be modeled as Gaussian random variables, one can use this interesting framework to formulate the equivalent, either stochastic, you can call it term with the stochastic version of the robust stochastic LP, or robust LP, or the stochastic version of the robust LP. We will stop here. Thank you very much.